but you get me as the replacement bus service. So we're talking about an idea that we call Non-Newtonian Hardware Design. Catchy name, name-based research. So the problem here that we're trying to look at is we have lots of accelerators out there, and we're thinking about a world where you perhaps care about the number of chips that you buy or you operate for some particular reason. And so you have an accelerator which is monolithic, which is performing some function f, and this should take less time than running in software. But if you think about the fact that you have a limited number of chips and your accelerator might break down the road, might malfunction, security problem, or other thing, you're going to have to fall back to software and run your code in software instead. And so this now requires that you have a software implementation of all of the hardware that you had. Maybe that software is going to run inside your operating system. Good luck having this massive additional piece inside your operating system to perform the accelerator's function. And it's going to be a lot slower than your accelerator was. Right? So it's going to burn more power, you're going to spend more dollars. And the alternative is you go out there and you buy more chips, and that burns more carbon, and that is going to have other implications. So in particular, if you have a big difference in performance between the accelerator design and the software implementation, you're going to see some serious issues if you need to stop using your accelerator because it was some sort of problem. And so we're trying to ask, what if we could build an accelerator where even when we have a hardware malfunction occur, we could fall back to software only for what we needed. How would we go about making this design? And we're going to talk about this from a high level. So in the current model of the world, you have monolithic accelerator, F, you're running some software thread, you go out, you call the accelerator, does what you want, and it sends you your data back. Now, in the simplest case, if we wanted to have some form of modular acceleration, then we would go and perform a bunch of calls to a lot of smaller accelerators. It doesn't really sound exactly ideal, but what it does enable us to do is when we have a failure occur, we can simply run that one piece in software, and we don't need to throw the whole thing back to software, just the piece, the modular piece that we're going to have the problem with. This still has this downside that we're going constantly back and forth to software. It's not really ideal. There's a lot of overheads that come along with calling accelerators today, particularly fixed function ones. And we're trying to maintain correctness here with respect to the original design. We are trying to assume that we're going to have the same semantics for each of our pieces. So what we are trying to propose to do is build a kind of accelerator design workflow where we are able to break our accelerator up into all these pieces, but we don't need to fall back to software for every single time that we're going to make a separate call. And so when there isn't any fault in the system, you can just run through a nice, low latency, high throughput design you would normally have, and then only fall back when a hardware failure occurs. And so in the particular instance where this would happen, fall back to software just for that one piece. Everything else is still running much better. So, questions that we have at this point, how do we do this? It seems like it's a good idea to pipeline quite deeply here, like come up with a bunch of separate pieces so that if one thing fails, it's only a small part of everything that we need to do. Could we go beyond simply pipelining the design and have, some kind of branching, other kinds of data flow in this picture, and, asking questions about what sort of problems this will introduce. Now, we had a paper in ASPOS this year which kind of inspired us to do some of this, which is called Cohort. And the Cohort mechanism is essentially a way for you to be able to call accelerators and chain together accelerators using software threads. That paper was first authored with Henry, who gave a couple of talks earlier on. And so the idea is that you have software shared memory queues as your mechanism for communicating with your accelerators. We find this gives better performance than using an MIO, than using DMA. And so in that setting, we have a nice clean mechanism for muxing between hardware-based connections between the subcomponents of your accelerator and muxing back to software and using our software shared memory queues. And so what Guy implemented, and I'll note Guy is a second-year undergraduate who is very advanced and implemented this himself, was a three-stage mixed multiplication accelerator. And he's trying to kind of measure the cost of, I'm running in software, what would happen if I took the naive approach what would happen if I had the NNHW approach, and what would happen when I had a fault occur. As a very short pipeline, we're not going to see kind of the full theoretical longer effects here, but we do see that if we went for the modular acceleration, where we constantly go back and forth from software for each accelerator, we get about a 5x improvement in performance. If we have the non-Newtonian approach, we get further improvement in performance because we don't need to go back and forth to software all the time. So this is kind of a more ideal here. But if you did have a fault occur in your middle stage here of your 3-stage pipe, that you would be able to fall back into software just for that middle one, and it would be a lot faster than if you ran in software still. And so this could be advantageous, right? This introduces problems. It doesn't just solve them, right? So we now need both a hardware description of the code and a software description of the code. This means that we need a semantically equivalent software implementation of each of these pieces of the pipeline, which is something that we wouldn't normally have in hand. And so something that Guy's been interested in looking at the moment is, could we go from software down to hardware and have a single description that came from software, or could we go from rather our hardware implementation in the backwards direction and get our software implementation? And so this may be unsurprising for those of you who know that I'm from the University of Glasgow. Functional paradigms are a great way to consider doing this. And there's a recent functional HDL which we found quite interesting, which is called Shakeflow. And this was also published at ASPOS this year. We're kind of asking, could we go from functional hardware back to functional software so that we would have semantically equivalent implementations of these different stages? And so we have a good figure here which kind of shows you, if you know Rust, I guess this would be very readable to you. I don't know Rust, so it's not very readable to me. Implementation in Shakeflow of matrix add. If you actually go and look at kind of the pseudocode of what you would need for functional program, or like an OCaml implementation, you can kind of map across between the zips and the maps here and see you're doing the same functional patterns. Maybe this would be easy for you to then push into software and be able to figure out your functional part. Another thing to bring up here is we don't necessarily need to fall back to software. Perhaps we could have some hot spare FPGA lying around on our chip. It seems like a good idea. You could bring out your hot spare FPGA and just reprogram it for whatever the stage of your accelerator that fails is, and then that might enable you to get much closer to the throughput that you would get with your ASIC. Of course, then you need to be willing to not use this hot spare FPGA for anything else in the meantime. I guess IBM sell machines that have like entire hot spare clusters of CPUs, so maybe we're all okay with that. And so we have a couple of possible workflows we could take going from a functional hardware description. In the top case here, we would have a software fallback versus the actual ASIC. In the bottom case, we would have an FPGA fallback versus the actual ASIC. And so from here, what we're working on to put together a paper is looking more at kind of the effects of pipeline depth. How can we do this translation? Could we build various kinds of reusable components, doing some high-level modeling, and so on. But that's all I will say here for now. Thank you.